All right, it's 2:02 now. I think we can get started. So hello, everyone. Welcome to Ask Seminar series. I'm John, the seminar coordinator. I will be the moderator with Ms. Kathy Medney, who is our communication specialist. And our director, Dr. Ed Williams, also joined us. And Anna will be introducing the speaker before he gets started. So this seminar will be recorded, and the recording will be published on our YouTube channel. So be free to check it out. And the question session is after the presentation. So we encourage you to ask a verbal question, or you can chat us your questions. And before we get started, I will make an exciting announcement that so next Monday at our regular seminar time, we will have the first in-person seminar for a long while. And so we encourage you to come attend the seminar. It will be held in our large conference room on the 4th floor of ASIC building. And you will find all the details in our seminar announcement. And then seminar will be given by Dr. Ariana Sutton-Greer from USGS. We will encourage you to come and talk to the speaker. And we also will provide refreshment for this seminar. And so let me turn this over to Anna. So Anna, please go ahead.
Okay, well, it's my pleasure today to introduce Dr. Ali Omar, who's the Acting Deputy Director of Science at NASA Langley Research Center. He received his Ph.D. from the University of Illinois at Urbana-Champaign in 1997. Upon graduation, he spent a year at the UIUC Electro-Optics Systems Laboratory as a postdoc working on retrieval of temperature and aerosol profiles from data of NASA's Lidar in space technology experiment. Dr. Omar is a science team member of the CALIPSO missions and led the CALIPSO aerosol classification algorithm development effort. Research interests include development of intelligent classification methods for remotely sensed geophysical parameters, development of algorithms to determine aerosol properties from spaceborne LIDAR data, and investigations of aerosol subtype distributions and their effects. Dr. Omar is a Fellow of AMS and has served 2 terms as the AGU Secretary for the Global Environmental Change Section. So thank you, Dr. Omar, for joining us today, and we are very much looking forward to your talk.
Thank you very much, Ellen, for that introduction. I will share the screen now and start the presentation. Hopefully I can find. Okay, can you all see my first slide there?
Yes.
Okay, so thank you, John, for the invitation, and Kazi for making this possible. I'm Ali Omar, and the talk I'm going to give, a lot of contributions came from the LIDAR Science Working Group at Langley, NASA Langley, over the last maybe 15, 20 years. And so starting from the very, very beginning, I am just going to assume that we don't know much about LIDAR and talk about some very basic principles. LIDAR is a tool that can be used to detect a wide range of features in the atmosphere, including things like clouds embedded in aerosol, very thin cirrus clouds, subvisible, that we really can't see with the eye, but the LIDAR can pick up, depending on the wavelength you use. We can also see multiple levels of cloud decks. I don't know whether you can see my mouse. Can you see my mouse? No?
Yes, yeah, we can see it.
Okay, so you can see through multiple layers of clouds, and this is a very unique feature of the LIDAR that enables you to penetrate through features and see features below some very thick features. And I like to say that for long-range transport of things like dust, LIDARs are probably the best because they tell you what altitude the plume is at. and as such, you can track it over long distances, and you can provide the initial conditions for any type of transport modeling of aerosols. And then finally, polar stratospheric clouds are good candidates for LIDAR because they tend to be very thin and wispy, and sometimes occur in multiple layers, so you can penetrate through the cloud and see pretty much all of them. So these are all the advantages of LIDAR. Of course, the main disadvantage of LIDAR is because it gives you a full vertical picture. The footprint on the ground is really small, so it doesn't really have any kind of swath. You're seeing about 100 meters at a time on the surface. So this is a typical LIDAR image. You have, this is an example from CALIPSO. You have CALIPSO orbiting at about 705 kilometers above the Earth's surface and sending signals in the green channel, 532 nanometers, and the red channel, 1064 nanometers. Those signals interact with different features. In this case, there's a cloud at 14 kilometers. It interacts with that cloud. Some of the light is backscattered to the telescope of the system, and then some of it penetrates that cloud and goes and interacts with aerosols closer to the surface, maybe at between 4 kilometers and the surface. And then some signal makes it all the way to the surface, and then you get a pretty strong backscatter from the surface. So as you can see in this picture, you can see clouds at 14 kilometers. You can see a pretty thick 4-kilometer layer closer to the surface. This is a profile that was measured off the eastern coast of Africa near Madagascar. And at this time, there are pretty strong tropical convective systems near the equator. As you go closer to the equator in this region, you have those convective systems. And then before that, you're coming through the Arabian Desert and all the dust that is advected off the Arabian coast. And so you can see very clear pictures of those features because of the aerosol of the LIDAR's ability to send this laser through all these features. And then you can tell where the features are by the length of time it takes the signal to go back to the telescope. So it's a ranging capability. And so NASA has had several LIDARs in space over the last, maybe 30 years. 35 years. The first LIDAR in space was LITE. This is the one that Dr. Williams mentioned in my introduction. I worked on this very first system, not when it was launched, but the data much later, maybe around 4 or 5 years after it was launched. That was the LITE instrument that is shown here. It was a proof of concept to show whether we can actually do laser measurements from space and look at features and define those features. That experiment enabled us to design CALIPSO in 2006, in which I also was involved. This is probably the first mission I worked on after graduate school, from the very beginning of the mission. And it was designed to study clouds and aerosols. And then there was a CATS mission between 2015 and 2017, which operated intermittently in space. It was on the International Space Station, and it was a demonstration of small LIDAR systems, what they refer to as affordable payloads on the International Space Station. And then we had other missions. The JEDI mission is an ecosystem LIDAR looking at biodiversity and ecological forecasting. And so that has been operating since 2018. And then the ICESat mission, which is really looking at the thickness of the ice in the polar regions, especially. And that mission this is the second time it's launched. The first one was 2003. And then the second one, which is still operating, was launched in 2008, and it's used for mapping snow and glaciers. But it also has, as I'll explain later, a pretty significant atmospheric component that you can use. So CALIPSO, maybe the main LIDAR that has produced a lot of data and a lot of discoveries over the years, is a LIDAR that is got two wavelengths. On one of the wavelengths has parallel and perpendicular channels, so you can get polarization. And the other LIDAR is the 1064. The other wavelength is the 1064 nanometer longer wavelengths. And then the mission had a wide field camera, which gives you some image of the context you're looking at. And because this mission was a joint mission between NASA and CNES, the space agency in France, they contributed an imaging infrared radiometer, which produced pretty large swath products. And so in 2006, it was launched in 2004, April. In 2006, we got the first image of CALIPSO, and this is the very first light of CALIPSO. The whole team was very excited to see this because we saw all the features we expected to see, like water clouds closer to the surface, cirrus clouds a bit higher up, around 10 kilometers. And then there was a volcano, so there's a pretty distinct volcanic aerosol around 18 kilometers above the surface, and then several aerosol features near the surface. So initial first light was in July, and then in September we released some of the browse images, and 6 months later we released all the science data to the community, and several discoveries and publications started from that. So the CALIPSO data, some of the processing involves looking at the backscatter image to identify the features. In this case, we see an aerosol feature here by the yellowish color. The reddish color is some pretty strong backscatter. The whitish colors are even much stronger white backscatters, which are usually a result of clouds. And so you can also see the higher features around 15 kilometers, and so those are clouds. So the first thing we do is develop the cloud mask, separate the aerosols from the clouds, and that's done by an algorithm that was designed by Zhao Lu, where he looks at several parameters measured by CALIPSO and uses those to intelligently discriminate between the aerosol and the clouds. And then another algorithm looks at, say, this aerosol chunk here, and tries to determine what parts of that aerosol are smoke or polluted continental or marine aerosol, as the case may be. So we had, like, initially we had 6 types of aerosols that we could identify from the CALIPSO data. I think the team has increased that to 7 in later versions of the data. Initially, there wasn't much validation that we could do. So we looked at things like the context. For example, it's flying over Southwest Africa at a time between August 9th and 18th, where the MODIS image shows us that there's a lot of fire and burning. And so the identification of smoke in this region looks quite reasonable because of those fires raging, and that most of the aerosols in that region would either be a smoke or some smoke mixed with dust, what we call polluted dust. The cloud aerosol transport system cuts on the space station. Only some of these images show similar types of retrieval as I presented earlier from the CALIPSO. Again, we can see structures of clouds, dust, and smoke. And we can see that you can tell the dust that's lying below the cloud because you can penetrate the cloud completely and identify the dust below it. So this image shows quite well how you can tell different types of features just by the sheer ability of the LIDAR of the laser system to penetrate. As I said, CATS operated semi-continuously on the ISS between 2015 and 2017. It just demonstrated the feasibility of having an instrument on that platform. And so, right after we launched, there were several studies about dust. Some suggesting that dust was doubling over much of the globe during the 20th century. We know there are many papers that show the contribution, the effects of dust on aerosol direct and indirect radiative forcing. And also in 2006, there was a big campaign to look at the African easterly waves and the development of tropical storms and hurricanes from the NASA, I think, maybe NSF and NOAA had some participation too in the NAMA mission that looked at the genesis of tropical storms. This was happening right after CALIPSO was launched. And then some papers suggesting that dust emission rates have continuously increased since the 1950s. Then Hongbin Yu at Goddard did a study that showed dust as a source of nutrients for both phytoplankton and also the Amazon basin that received a lot of publicity. And so we realized that CALIPSO's measurements of dust properties of all things are really quite robust, and the length of the record is significant, both seasonally and interannually. And so we wanted to look at some in-depth studies of dust and get measurements that may be useful for simulation and validation of transport models. So one of the first studies we did was to look at a dust plume that was generated off the coast of Africa. This is the Sahara Desert up here, and see, looking at about 9 orbits as that dust plume is advected and transported across the Atlantic. And we can see day by day that plume can be tracked very well by these CALIPSO orbital tracks that show the plume and where it is and how it is growing and how it's beginning to break up, and eventually how it is deposited closer to the surface in the Gulf region. And so around this period of August 25th, 28th in 2006, there was another field campaign in this region that had aircraft, surface measurements, and also modeling of the dust transport. We used those measurements along with CALIPSO's measurements to gain very good validation of the CALIPSO measurements, and also to verify the transport of the dust from the Sahara. We did more studies looking at transport and source regions in Africa and the Mediterranean region, and also South America for dust, and looked at how the properties change from the source as it's advected across. And you see that if we look at just the volume depolarizations, that there's a pretty consistent, the changes are not as large as has been shown by other studies also for the pure dust cases. And then when we look at times when this dust is mixed with smoke, when smoke happens in parts of Southwest Africa, the same transport of the dust, we see that there's quite a significant change in the volume depolarization. Actually, it goes from 0.012 to 0.06, which is quite a large factor of 2 decrease in the depolarization, which shows that the particle is becoming more spherical. Maybe it's becoming coated with other pollutants or water vapor as it's transported across. So it's being transformed much more than the pure dust in the previous case was. And we also looked at different times where you had a lot of dust in 2009 and 2010, and then a very quiet period in 2010 and 2011. And so we could see the dust anomalies, and some of those were pretty much coinciding with some of the ENSO cycles of that time. As I said, Hongbin at Goddard looked at the transport of dust from the African continent into the Amazon. And the Saharan dust feeds the Amazon rainforest with an estimated 22,000 tons of phosphorus. And that phosphorus is usually leaked by the rain. So the plant does not have, would not have essential nutrients if it was not replenished every year by the transport from the Sahara. But how is that transport changing with climate change? We don't know exactly, but at least we have a way of estimating that using the work that Hongbin Yu has done to look at transport using Lidar, where he can estimate the fluxes accurately because of the vertical resolution of the transport into and out of the Amazon, and estimate that about almost 28 million tons of dust is deposited, and that 28 million tons contains about 22,000 tons of phosphorus, which helps to replenish those forests every year. And also he did this by season to show that the influx is largest during the spring months. So LIDAR observations of dust also have been used in Europe in air quality modeling because CALIPSO overpasses show exactly where the dust is, and also one can make an estimate of the quantity of that dust if you merge the passive two-dimensional images with the vertical image to obtain a 3D estimate of what the dust plume size is for modeling, and also just to estimate how much dust is transported every year to those regions. CALIPSO has been used for smoke and fires. In this case, this is a new fresh smoke from the Wallow fire in Springerfield near Arizona. The same smoke was observed by MODIS 9 hours later. But the important features here are that the CALIPSO image provides you the height of the smoke plume, which is very important for initiating your air quality model and to determine the impact on air quality from wildfires and burning. Another image in 2016, this fire in Canada, Fort McMurray. Again, this was a case of a smoke plume that had broken up, but CALIPSO affords the estimate of the plume height of the main parts of that plume as it breaks up, and that information is again useful for air quality modeling, given your knowledge of where the clouds are, where the plumes are, and also the dynamics of the system. It improves the air quality skills quite a bit. Over the years, CALIPSO has developed a good database of vertical distribution of cloud fraction. All this is information that we didn't have prior to LIDAR. And now we can see the cloud fraction both at night and at daytime, and also over land and over ocean. Another thing I didn't mention about the LIDAR estimates of 3D properties is that the LIDAR is insensitive to the type of surface because all the measurements are done prior to the signal reaching the surface, except for the features that are very, very close to the surface. The other features are relatively unaffected by the surface type, whether it's a bright surface or it's snow or it's vegetation or water, has no impact at all on the measurements. The other thing is that the nighttime measurements are actually better than the daytime measurements for backscatter LiDAR, because the nighttime measurements are less noisy because there's no solar background. And so we get measurements, diurnal measurements also over all types of surfaces, and we get good statistics of some of these properties. This is another case where we developed droplet radius, extinction coefficients, cloud water content, and droplet number concentrations from the LiDAR data for the globe for both day and night, and also over all types of surfaces. And then I want to discuss a few other additional products that we could get out of the LiDAR data, which we had not planned to do. Just the ingenuity of some of the scientists who started looking at the backscatter as a function of the surface deformity, or the sea surface Fresnel reflectivity. And so the surface deformity of the ocean surface is related to the wind speed. And so from the surface backscatter, you can determine the wind speed if you know your atmospheric attenuation and also the reflectivity, the Fresnel reflectivity. You can back out the mean square wave slope of the ocean surface, and from that you can get an estimate of the wind speed from backscatter LiDAR, in this case CALIPSO, and compare that with an instrument AMSARI, which was designed to actually measure the wind speed, and the comparisons are pretty good. If you look at the differences, mostly highest near the coastal regions, but in the deep ocean, you get a pretty good agreement between the two. You can also use the LiDAR together with the radar to provide very complementary measurements of cloud occurrence and cloud detection. In this case, as a function of temperature, we see that the cloud detection is highest. In the critical -20 to -50 degree temperatures, you see that the LiDAR and the radar detection capacity, capability or probability of detection, if you use both instruments, is much larger than if you're looking at LiDAR only, which will give you a very good probability of detection at the top, and radar only, which would give you a good probability of detection at the bottom. And so this is a paper by Hensfield in 2014, in which he showed that the LiDAR and the radar detection are really much more improved between in the middle of the cloud systems. We used LiDAR, especially in particular CALIPSO LiDAR, and the vertical profiling capability, and also the cross polarization of the signals from below the ocean surface, to estimate the particulate organic matter below the surface of the ocean, using the diffuse attenuation that we get from the LiDAR depolarization. In particular, the particulate organic carbon was retrieved from Cali of spaceborne LiDAR, and this compares, as you can see in these images, quite favorably with the MODIS retrievals. This work was pioneered by Young at Langley, and he worked with Berenfeld at Oregon State University to develop some of this particulate organic carbon products. LiDAR also can be used if you know how long a LiDAR signal travels within the snowpack. In this case, this is signals from ICESat-2. We know that the average distance of the photons inside the snow is about twice the snow depth, and so you can get the snow depth from the length of travel of the photons within the snow in the snowpack, taking into account the multiple scattering within the snowpack and most of the other parameters that you measure. You can back out an estimate of the snow depth within the snow. And when you compare this to the IceBridge measurements, IceBridge aircraft measurements of the snow depth that are relatively quite accurate. And so if you look at that as the truth, you can compare that the different IceSat-2 wavelength, blue, green, and black, give you reasonable estimates of what the measurements of the snow depth from the IceBridge airborne snow product is. So that's another product that we actually never planned for, but is a pretty useful product, because knowing the snow depth gives us information about the water content of the snow, and that's important for water resources. In about 2008, 2009, Young again came up with this method where you could estimate the extinction through an aerosol layer. If that aerosol layer was sitting above an opaque water cloud, and so you could compare the integrated attenuated backscatter through the aerosol layer and compare to that of the region where there is no aerosol at all to determine the optical depth of that aerosol layer. And that's really important, because normally we have to make an assumption about a LIDAR ratio. So any LIDAR person can tell you that if we don't have to make an assumption about the LIDAR ratio, we get extinction measurements that we have a lot more confidence in. And in this case, this is a new tool in the retrieval techniques for LIDAR that the community has as a result of some of the work that was done in the last few years on LIDAR. LIDAR also can tell us something about melting points over sea ice, especially in the Arctic. In this case, we can see that these are returns from below the surface up to about -4, -6 meters below the surface. And we see that there are regions where the returns are not there, and that tells us that the pond is melting in those regions, and so we can tell exactly the depth and the width of the melt from looking at LIDAR returns below the surface. We can use LIDAR to train other passive sensors. This is a comparison between CALIPSO's height of features and Parasol's height of the same features. And we can see that those are very noisy and not really close to the one-to-one line. And when we look at, this is for the Rayleigh pressure, when we look at the airband pressure from Parasol, the comparison is even poorer. But if we train the polder instrument with LIDAR data, we get relatively accurate measurements of the centroid height when you compare that to the CALIPSO centroid height for both cases. And so that's a case where we can improve measurements from other passive instruments if we have a good LIDAR measurements in the vicinity. IceSat-2, we have used that to look at the height of crops. Remember, IceSat-2 is mainly designed to study the surface, the height of the snow on the surface. In this case, we can study the height of crops and determine the yield of the crops and the health of the crops. This is a case of an irrigation project in Egypt, and we're looking at wheat plants between 0.8 and 1.2 meters, which is considered for wheat growth to be very healthy. And then we can see during the periods when this have already been harvested 6 months later, that the plants are no longer there. The same thing for crops, for corn in the same irrigation project. Again, we can see that the corn plants can be identified, and then after the harvest that they are gone. In both cases, the LIDAR gives us a pretty good estimate of what the height of those plants are. And this is important for not only studying the health of the crops, but also estimating the availability of food, things like drought, estimating the possibility of drought just by looking at the satellite estimates of crop health. If we look at CALIPSO and ICESat complementary, CALIPSO will give you the estimate of the height very close to the surface and maybe a few meters below the surface of deep water, shallow water. The ICESat-2 measurements will go below that and actually show you the reef edges and the sea floor for a complete bathymetry picture from above the surface to about 30 meters in this case below the surface. Another application that we have used, which is not a dimension, but this is more of a temperature. We can estimate the temperature from the UV wavelengths of any LIDAR system. In this case, this was LITE. We saw in these several orbits in South America, in the tropical regions, that there were these very high clouds, about maybe 15 to 20 kilometers high, very thin cirrus, persistent. Because of the very high cirrus clouds, we wondered whether the temperatures are comparable to polar temperatures. And if so, do these clouds behave similar to PSCs? And if they do, what are the implications for ozone chemistry and radiative transfer? And so we know that cirrus cloud surface area is suitable for heterogeneous reactions of otherwise inert chlorine-containing compounds such as HOCl into reactive forms of chlorine that could potentially destroy ozone. So we wanted to see whether these temperatures are closer to the 190, 195 degrees that are most suitable for those reactions to take place, and where those reactions could take place also in the tropics, just as they do in the poles. And so the first thing was to remove the aerosol effects from the backscatter profile of the light data, the molecular backscatter, which is most pronounced at the 355 nanometer channel, the UV channel. And then we can derive temperature profiles directly from the molecular profile, which is related to the density, and from the ideal gas law, the density is related to the temperature. And so we can determine temperature profile based on the LIDAR molecular backscatter. And so this is some of the results that we obtained, and indeed some of the temperatures are really cold. And if the same species are present, then we expect the same reactions that we see in the polar regions, because those temperatures are also very cold. And so that was in a paper on LITE that I published with my postdoc advisor during my postdoctoral days at Illinois. looking at those temperatures. But that's another application of lidars. At least for me, that introduced me to lidar. So we can go from temperature to cloud. So the whole gamut of parameters are important for weather and dynamics and convection can be obtained from carefully designed lidar measurements. And so to summarize, LIDAR successfully demonstrated the utility. LITE demonstrated the utility. This was the one on the space shuttle in '94. Demonstrated the utility and feasibility of space LIDAR, and ushered in the successful era of other NASA atmospheric lidars such as CALIPSO, CATS, and ICESat. CALIPSO and CATS in particular have initiated a new era in Earth remote sensing with key profile observations of clouds and aerosols. These discoveries have enabled through these observations are revealing linkages between clouds and circulation and advancing our knowledge on cloud and aerosol interactions. CALIPSO, in particular, subsurface ocean measurements have ushered in a new era of ocean LIDAR observations that we did not have in the ocean sciences before this. ICESat-2 has demonstrated a number of innovative key terrestrial applications, not the least of which are snow depth estimates, ice melt ponds, and agricultural crop heights. And building upon the great strides made with CALIPSO, NASA is pursuing new international Earth observatory called the Atmospheric Observing System with additional LIDAR capabilities, and advances in the last 5 years in high spectral resolution LIDAR and dial systems for aerosol absorption and trace gas measurements for ozone, water vapor, and methane suggest that these are getting ready for space applications and enabling progress in climate studies and extending the benefits to society. So that's really the gist of my talk. I will take questions. If there are questions in the chat, maybe you can unmute yourself and ask the question, and I will stop there.
Thank you, Dr. Omar. Just as he said, you can go ahead and unmute yourself to ask a question. I see David Wynn typed in a question a couple minutes ago. David, if you have a microphone, please feel free to ask a question now. Or if not, I can just read it out loud. Oh, there you go.
Okay, I was just wondering, with all the issues around the Colorado River and the different types of irrigation techniques, can you kind of study the aerosol loss off of the different types of irrigation techniques that go on in that part of the country, Arizona, I mean, there's massive amounts of crops being grown there. And I mean, just can you study the aerosol loss or the water loss?
The aerosol or the soil loss?
The aerosols, like, you know, they have the circular irrigation techniques, and so they're just spraying water into the air. How much of that water is just lost to the atmosphere? And
okay. So one could measure the optical thickness of the atmosphere, right? And that optical thickness is a function of how much stuff is in the atmosphere. Mm-hmm. And in this case, how much water droplets are in the atmosphere. The LIDAR could definitely tell you what it is. For example, water droplets would be pretty spherical, and if you had a depolarizing LIDAR, you could get an idea of what percentage of particles are non-spherical, and that would tell you that's water vapor. And so you could pretty much tell how much of that is lost in the air. Correct.
Yeah, I only bring up the question is, I mean, some irrigation techniques may be better than others, and so you would like to choose an irrigation technique where you have the lowest water loss.
Correct. So correct. So that's a question of efficiently using the water for irrigation. On the other hand, it's a water cycle, right? It goes up, it comes down. So
yeah, but it's going to come down somewhere else.
Exactly. That's true too. That's true, David.
Yeah. Anyway, it was just a thought.
Yeah, I definitely LIDAR can measure that, and there are lidars that specifically measure water vapor. So you could see that when they do the irrigation, the water vapor profile changes in that region, and you can estimate how much water is what's the difference in the water vapor content between before irrigation and during irrigation, and you can tell how much you're losing.
Yes.
That can be done, definitely. Yeah.
Yeah, great. All right, thank you.
You're welcome. Zhangqing?
Yes, Ali, thank you so much for the so well summarized CALIPSO, what can be done. I was on the early science team. I remember the mission was much less limited in terms of scope of application, and you show that CALIPSO can almost done anything beyond the traditional backstream LiDAR can do. Of course, there's a lot of genius ideas, and I just wonder, these days we are talking about the future missions, and the so well done with CALIPSO will mean anything resistance, because someone from outside the community may think, oh, you have done so much things that others, HSR and DAO system are supposed to do. I wonder if there is any such kind of argument. And my second question is about your own expertise in the classification of aerosol type. With CALIPSO, we have limited information, even though we have 2 channels and also have population capability, but they are still not enough to really do a classification. So I wonder what other ancillary information have you brought into classification of aerosol types?
Thank you, Zhangqing. 2 very good questions. The first question is, do we get resistance from the policymakers about launching an instrument, since CALIPSO has done everything? And the truth is, CALIPSO has not done everything. CALIPSO has done quite a bit, but other instruments like HSRL can do a lot more and can answer your second question, because CALIPSO, as you know, and you have stated, is quite limited in information. And so we're really guessing at the types. HSRL is much better at giving you more objective types. And also HSRL does not need to make an assumption about the LIDAR ratio to calculate extinction. So you get extinction values that are accurate. So for these 2 reasons, HSRL is really important to be considered as the next instrument if one wants to make real progress in these measurements, and also in the amount of information that we have. Having said that, it's still important for us to continue getting measurements from a LiDAR of some sort, and that CALIPSO measurements do not stop here, because the international community, the science community, needs those measurements, has relied on those measurements for the last almost 20 years to improve their models, and so there'll be a big gap if we don't have that. Luckily, the Europeans are launching EarthCare very soon, and so there will be some overlap between those measurements and the next NASA deployment of a LiDAR.
Great, thank you.
Thank you. So we have Lauren Zamora and Ellen Williams first. Go.
Yeah. Oh, hi. So I have a little bit off the wall question. Early in your talk, you showed beautiful ability to penetrate through cloud cover and then actually get a return from the surface as well and detect the surface. And then later in your talk, you showed really nice results for measuring the height of crops using a LiDAR reflection. And I'm wondering, I suspect there's some sensitivity issues here, but could you do the same sort of crop experiment under cloud cover?
Yes, you can do under cloud cover, depending on, you can't do those measurements under a full-blown convective system with very thick clouds and very dark, clouds with a lot of water vapor would be opaque to the system. but most of your wispy stratus, stratocumulus clouds, you can penetrate very easily and get to the height of the crops all the time. So yeah, so that's not a limitation.
Great, thank you.
For that measurement. Thank you, Ellen.
Yeah.
So can we go to maybe, I don't know what the order of the hands are.
It's
So
Lauren
Kazi,
first.
can you call the
Yeah,
call out?
of course. Wait, can you hear me still?
Yeah, I can hear you.
Oh, okay, good. Thank you. Yeah, so Lauren asked her question before Chris, and then we can go to Chris.
Okay, Lauren.
Hi, yeah, great talk. And it's so amazing all the work that you guys have done. I had two questions. One of them is, do bubbles interfere with the ocean observations if you have a lot of bubbles in the water? And then the second one is, do you know when EarthCare will launch?
I don't know the answer to the second one for sure. That date has been changing a lot. The first question also, I'm kind of stumped because I don't know whether bubbles seem to be very optically very thin, so they should be easily penetratable. I would assume that they don't interfere very much with the measurement, but I can check for you, Lauren. Let me see, or maybe you can write to me and then I can find the answer for you. I think my first hunch is that they are not, because it's really a film and then a space in between which has got air, so it shouldn't interfere too much. You may be able to, if you have several bubbles in a row, then the film might reflect some of the light because it's glassy and reflective. But I don't know whether it does interfere very much in the measurement. I can check for you.
Okay, yeah, I'll send you an email. It's something I've been kind of curious about, but over the years, but never like took the time to find out.
Yeah. I think it's a good question. I'll wait for your email and send it to the right person.
Thank you.
Go ahead, Chris.
Thanks, Ali. Interesting, comprehensive talk. I like it. Quick question. What types of data and where are they located such that you can download them? Is it in like basic form, or do you have science products that you can just download and then use, or do you have to basically process from first principles?
No, you can choose to process from first principles. We share the level 1, which is the very basic data, just range corrected, and that tells you where the features are. Then we have level 2 data that tells you, for example, is it a cloud, is it an aerosol, what's its optical depth, what's its extinction, what type is it. So that data is also available. All the data is of course available at NASA.gov should be a good entry point to the data sets, but you can also go to I'm stamping the first letter in the, well, go to nasa.gov and you'll find the links to the data, but all the data is available. The CALIPSO data is resident at the NASA Langley data center, and I can send you, if you send me an email, I can send you the correct link. But the data is available. You don't have to do anything. I think they may have some tools that they can give you depending on what application. You should be able to subset exactly what data for what period you want, or you can download all the data that we have collected so far. All that is available anytime, Chris.
Great, thanks very much.
Yeah, you're welcome.
We also had a chat question a bit ago. I will read that out loud.
Okay.
They asked, how instantaneously available are the science products from these NASA LIDAR, and what limits the availability?
Yes, that's a good question. And that's a problem that we've been struggling with for a long time. Between the time the measurement is made and the time it's available to the public, what you refer to as latency is about, now we have two products. We have an expedited product, which is available within a few hours after measurement. And then we have another product that uses accurate meteorological data to do the corrections. And because the meteorological data is not available immediately, we wait for it, and then we do the retrievals, and those products are about 1 day old from the time the measurement is done. But if you want a measurement that's a product that are developed from climatological meteorological data, which is they're not very accurate, but they're just the parameters that were measured for that area over the last maybe 10 years, climatology of a mean of those parameters that are used to retrieve the products. Those products are available within a few hours from our center, and we give those products to people who need answers immediately, first responders, or if a group is at a field mission and they want to find out what the approximate conditions are, those products are good for them, but also maybe good for somebody who just needs to get the result as soon as possible and does not want to wait for the next day to get those products. So yeah, so it's about say about 6 hours for the expedited, and also about 1 day for the actual standard products.
Thank you.
You're welcome.
Thank you. Does anyone else have any last minute questions while we still have Dr. Omar with us? Okay. Well, thank you so much, Dr. Omar, for talking to us today. And thank you everyone else for coming and showing up. I do just want to reiterate, while I still have you here, that we do have an in-person seminar next week. So I really want to encourage everybody to show up, talk to the speaker, enjoy some refreshments, support our series in person as we move into having some more in-person events finally. So thank you, everybody. Have a wonderful afternoon.
Thank you. Thank you, Ellen. Thank you, Kazi and John, and everybody else who came. Bye.
Bye.
Bye-bye.
Oh, and Dr. Lee, we will have the PowerPoint, well, everyone will have the PowerPoint available on the website. So you can just send John an email.